Oh, brilliant. I have a roommate who's from Winter Park, Florida, which I believe, is that in the similar area?
I don't know. Almost every single thing in Florida is south of us, so I'm going to say it's south.
Hi, this is Paul Shestople on the line. Sorry I'm late.
No worries at all. We're very excited to have you here or virtually on our campus. This is actually our first hybrid event, so if there's any technical difficulties, really sorry, you may have to bear with us. But the way we've got it set up, just so you're all aware, is I'm currently speaking to you from the podium in our lovely auditorium. We then have, I'm going to spin you around real quick and hopefully not knock all the microphones into the ground. We have a lovely audience. Audience, give a wave. Yay! Waiting for you, we'll have more people trickling in over the next 5 minutes. The way Berkeley works is we kind of start everything 10 minutes shifted off the hour to give people time to walk across campus and get to things. So yeah, the way we're probably going to have it is, well, not probably, the way we will have it is we'll stand here to do any kind of like technical stuff, make sure you guys are on the right screen with that. We'll also set up a phone pointed at the audience so you can like see the crowd whilst you talk. And then we also, as you can see on this call, have a bunch of students that will also be calling in over Zoom. So yeah, we're pretty excited to be doing this in a hybrid format.
Well, we're excited to be available, and thank you for for reaching out and setting this up. It's always great fun.
Yeah, it was actually quite funny. We had we run a class here as well about the new space economy, and we had oh, this is awful. His name's escaping, but he wrote the book, the New Space Economy is Open for Business, and he was talking about like, oh, prominent companies in the industry, and he went, oh, this company called Made in Space, now Redwire, that 3D print on the International Space Station, and we were kind of sat there like, ah, yes, we know them. They're coming to campus this week.
Well, I am. I have to say, I'm looking forward to actually going to campus. That would be great. And in fact, today I'm in Denver, and I was kind of hoping to be able to swing. And I was in California earlier in the week. I was kind of hoping to swing up to Northern California, but it just didn't work out. I was in Southern California.
Well, I'm sure I speak for all students in this room that if you guys ever want to come in person to campus, we'll be more than happy to see you.
Nice, thank you.
Awesome.
Sorry, give me
I hear Alicia. Deejay, are you also on the line?
Yep, I was able to join in.
Ah, excellent. And so yeah. So let's see. And so you have people in the auditorium. What building are you in?
Yeah, so we're currently in the Sibley Auditorium. Are you a Berkeley grad yourself?
I am, yes.
Ah, so we're in Bechtel, just next to the Kresge Engineering Library, and we're just in like the big auditorium in there, which I have to say is a lovely space. When did you graduate?
That's the green building, yes, Bechtel. Isn't that the green? No.
No, I think is it Corey that's the green one?
Oh yeah.
Evans is the green one.
Oh, Evans, right. I was in physics, so I spent most of my time in LeConte.
Oh, that makes sense. LeConte's actually been renamed now. Because I'm not 100% sure, but apparently LeConte himself was not a person that should have had a building named after. That's now been renamed to temporarily Physics Building North. Hopefully you'll get a slightly more imaginative name in the foreseeable future.
For LeConte.
Oh, there we go.
Nice. Okay. You guys can kind of see the audience. I think we'll probably have. Look at us go. Okay. Hey, I wanted to say though, you guys can't see me. Paul, we got your swag bag, so I'm gonna hand out some of the Redwire swag that came in the mail earlier. Deejay, Alicia, it's so good to see you guys again. Thank you for coming.
Yeah, thanks for having us back.
And I think what what we should do is we should project the Zoom onto the screen.
We
for
can
everybody.
we can indeed do that. I was going to wait until they share screen.
Okay.
Do that.
Okay. Yeah.
Um,
Either that, or since people can't see who's talking right now, we can throw it up there.
Fair enough.
Okay. Yeah.
There we go. You will be able to notice if you look at the screen that people on the edges you can't be seeing very well. If people want to move towards the middle a little bit and do us a huge favor, you would be my literal best friend, and I would love you all forever. Go on. What absolute heroes?
Okay. I got some stickers, guys. I got Build a Bug, I got Redwire, and I got the logo. So should I do this? Should I just take one? Yeah. Oh, yeah. You can go. Yeah, that way. So, go back. Okay. Take one, pass it down. All right. So.
Brilliant.
You're welcome. All right. Okay, so, I think I'm gonna sit back.
On that note, I think as it's now approached 2:10, we can get going. So, Alicia, DJ, Paul, if you guys do you have slides or anything you want us to project up?
No, we didn't. We don't have any slides this time. We did give a talk last year. I don't remember, or maybe it was earlier. Yeah, it was earlier this year. We had some slides, and what we found is that we didn't. That there were some great questions, so we really didn't need to have any slides. So we didn't prepare any slides this time. But I will start by saying a little bit about myself, and then maybe if Alicia and DJ want to jump in after that, then. And it's not. It's just to give some context, and what we do here at Redwire and what we're interested in, and hopefully from there some questions will arise, and maybe things like, people pay you to do that, or no, really, that sort of thing. But so my name is Paul Shestople, as I mentioned. I am a Berkeley alumni. I got my an AB in physics from Berkeley, because of course it's Berkeley, so they can't give BAs like everyone else. It's got to be an AB. But I got a AB in physics and astronomy, and that was way back in '94, so 1,000 years ago. So I went off and got a graduate degree, and then I got a job at Stanford, working on an experiment, a satellite experiment called Gravity Probe B, and it was really interesting. I hadn't really been involved. Of course, we all have more than a passing interest in space growing up as when I was a kid, but I really hadn't thought about space as a career. As in part of my graduate studies was doing experimental cosmology, working on the WIMP on CDMS, which was at Berkeley and Stanford. But Gravity Probe B is this experiment, a satellite-based experiment to measure these two kind of subtle predictions of general relativity. And what I found is that that was very cool, right? Working on satellites is a challenge that is unique in the sense that once you launch your satellite, you're never going to see it again, right? And so you have to be very thoughtful, and you have to really plan well to make sure that you are prepared to deal with any problems that might arise on something that you can't physically touch. And so after Gravity Probe B experiment ended, I got a position at what was a company then called Space Systems Loral, and making geocom satellites, so geosynchronous communication satellites, there in Palo Alto. And I don't know, I put together somewhere north of 10 geocom satellites, and that was also very interesting. But then one day I saw Jason Dunn, who was one of the founders of Made in Space, give a talk on how 3D printing is so incredibly important for space travel. And I really had not been, I mean, I'd heard of 3D printing like everyone else, but I really hadn't thought much about it. And it just hit me like lightning. Of course, you have to be able to 3D print if you want to go to space, if you want to work on the moon, if you want to be on the International Space Station. And the reason is because you can't wait for a resupply mission, right? So you have to be able to print what you need right then and there. And this is, very important for the International Space Station. Also very important more important for the moon, but really crucial if you're going to go past the lunar, the cislunar orbit, because you can't wait for a resupply mission. And so, having seen that, I applied at Made in Space and got a position as a systems engineer at Made in Space, and that's what I had been doing both at Gravity Probe B and at Space Systems Loral. And that was great fun. And then about a couple years ago, we got this project called Archinaut, which is a satellite project to build a 3D printer on orbit. And well, actually, the 3D printer is not built on orbit. The 3D printer is launched, and then once we're on orbit, we'll print these beams that will support a surrogate solar array. And I went from being the systems engineer on that project to the program manager on that project, and have been having a lot of fun. It's very challenging, of course. It's extremely challenging to do something for the first time, but it is also a lot of fun confronting these challenges, which are both logistical and technical. And then also I get to work with, an awesome team of engineers and physicists and multidiscipline. I mean, we have electrical engineers, we have mechanical engineers, we have aerospace engineers and software engineers, and even a couple of physicists, not including myself. And so that brings me to today, where we're talking now.
Great. I don't know if you guys can hear me or not. Can you?
I can hear you. Yes, you're kind of low in the background, but yes, I can hear you.
I'm over here. I wanted to ask, so you're working with Deejay and Alicia on the same project, Archinaut, and what do you guys do, Deejay and Alicia, on the Archinaut project?
I actually don't work on the Archinaut project. Paul and Deejay have definitely been working on it for the last several years. I'm in another division. We make payloads for the International Space Station. Usually the cases has the ISS National Laboratory, so we normally work through them. There are some experiments that we do in other areas, and then some that actually get exposed to the vacuum of space. So anything having to do with the space station is my department. And then Deejay and Paul are out on the satellite side of the house. But like Paul was saying, they started with the company developing 3D printers and then branched off on new ways to apply that. And so I'm still working in the habitation environment on how to apply it on deep space missions, as well as how to develop other technology that would bring back to Earth and benefit Earth. So we're doing a lot of developments on materials specifically, trying to understand what we can make better in space and what's worth the cost of shipping up to space to process and then bring back down. Because if you think about crystalline structures and tissue growth and things like that, gravity really has a negative impact on that formulation. And if you think about materials as we're processing them, we have a lot of sedimentation effects due to gravity, so that wouldn't exist in space. So we're trying to experiment with different ceramics to have a more uniform distribution of strengthening particles, bring it back down to Earth. It's stronger, it can withstand higher pressures and different applications kind of that nature. So we have space for space and we have space for Earth. that we work on, and I had a little bit of a roundabout way of getting there myself, like Paul. I went to the Air Force Academy and popped out a pilot. So I was a pilot of 5 different aircraft in the Air Force for the first 14 years of my life, and then got the space bug after that. And Bigelow Aerospace was in my backyard. I was living in Las Vegas at the time and started working on the idea that we can have bigger and more ergonomic spaces if we use expandable materials rather than hard-sided materials. So I had a really great opportunity to work with them and learn all about the space environment before I made the move to Redwire. So got a lot of aeronautical in my background, and then switched over to the aerospace side of my degree just in the last 5 years. Cool. And DJ's got some special stuff in his background too.
My role on Archinaut is to do what Paul tells me to do. I'm his deputy, and so I have been involved with Made in Space and now Redwire for coming up on 8 years. I went to school for mechanical engineering with an emphasis in mechatronics, and the original intention was to go work with race cars, specifically Formula One. Until I researched that career path and realized that it was very short, and happened to find Made in Space via a Craigslist post for a job offering, and started my internship there and haven't left. And so since with my time at Made in Space, I worked on the first 3D printer that went up for the first time and manufactured the first parts on the space station. I joined at the tail end of that project, but it was still very exciting. And then my first full project was actually AMF, the additive manufacturing facility, which is now under Alicia's control. And that was my first real sort of soups to nuts engineering project. And it was very exciting. I learned a lot. NASA has a lot of safety documentation. They control every aspect of everything that an astronaut might touch. And as an engineer who was more interested in mechanisms and things, NASA seemed to be more interested in telling me all the ways that my mechanisms could hurt the astronauts. So that was an interesting learning curve there. But we took that and we started thinking about what was next, which led to what we call ESAM, which is the Extended Structure Additive Manufacturing Machine. And we developed that machine through a series of prototypes and culminating in a first of its kind TVAC test. We did that at the Northern California NASA Ames Research Center in the Engineering Evaluation Laboratory, actually in the TVAC chamber that was designed for the LADEE, the NASA LADEE mission. And so that was fun. That was about a 6-week test campaign, 24/7, always exciting. And we demonstrated that additive manufacturing of Ultem could work in a simulated LEO environment. And to our knowledge, that's the first time that's ever been done. And so that was a huge, big step for us. And we took that and started working on what we called GBMASH, which was ground-based manufacturing assembly system hardware. If you stay in aerospace, you will learn quickly that acronyms are everything. And that test was to demonstrate the robotic assembly and manufacturing side of the sort of Archinaut suite of technologies. And so we had a six degree of freedom robotic arm inside of kind of a playpen, if you will, that had a bunch of things like electrical connectors and nuts and bolts. And it also had a remotely manipulatable extruder for a 3D printer. So essentially we took the 3D printer away and just kept the extruder part that a robot arm could hold, and demonstrated additive manufacturing again in a TVAC, a simulated LEO environment, but as well as all of the robotic assembly. And we took both of those two pieces of technology and kind of smashed them together, and we've been making that into Archinaut One, which is the first spacecraft that's going to demonstrate both manufacturing in space of a structure that will deploy a solar array, but also robotically manipulate components of that satellite to allow kind of what we call orbital replacement unit demonstration. So we're going to take the manufacturing device, actually physically remove it from the spacecraft, put it back down into a different location, reload it robotically, and then print a second structure with that. So we're really excited. I saw a couple of heads nodding, so I think some of you guys have maybe seen the videos that are on the internet of those of the ConOps we have there. But that's where we're at, and we're really excited, and you know we're also pushing pretty heavily on what comes after that. Even bigger structures, more advanced manufacturing techniques, different applications for satellites. So it's a really exciting space to be in.
If I may ask, what's the benefit of like detaching and then reattaching to that mechanism?
Yeah, that's a really good question, actually. Early in the project, a lot of our engineers asked the same question because when we were looking at the original concept, they said, hey, why don't we just put the manufacturing device on a turntable? Because that would have demonstrated the same net result. But we really believe that robotics is on a core path for all of our expansion back into the stars with lunar missions and Mars and beyond. Really demonstrating robotics, not only that, but cheap, affordable robotics. You know, I think the extent that we have right now is something like the Canada arm on the ISS, and that's a behemoth, and it's a very human in the loop controlled arm. And so what we're doing is kind of sort of paving the way, both with what we're doing on Archinaut and also what we're developing at Maiden Space Luxembourg. Well, I guess it's part of the Redwire group now, but our Luxembourg office is developing an arm kind of around those concepts, a very affordable robotic arm, so that we can demonstrate all kinds of robotic manipulation techniques and largely the assembly side, right? Because crew time is very expensive. It's very risky to put an astronaut out there. Sometimes they can't get out far into the depths of space where they need to be. So if we can send cheap robots, we can get a lot more done a lot quicker. So yeah, that's why we chose to put a robot arm in there, was to make sure we stayed on that roadmap.
Yeah, that was a really excellent explanation, Deejay. But let me add on to that a little bit. You know, so one of the things that Redwire is really interested in doing, and I think it's probably true of the people in the audience today as well, is really working to make low Earth orbit human friendly, and make Earth or humankind a multi-species or multi-planetary species. And you know, if you look at the history of why humans moved into a new area, it's not because of tourism, which is great, and I certainly don't mean to knock, you know, people, those companies that are providing tourism opportunities, but really what drives expansion is job opportunities, right? And so you know, the payloads that we are developing, that Alicia's division is developing for the International Space Station, those aren't just for the International Space Station. They can be used on any orbital platform. And those are really the things that are going to get people to, you know, to go up and have jobs in space. But at the same time, we also have to be very cognizant that space is dangerous, right? Not only, as Deejay mentioned, crew time is very expensive. It's, I don't know, I've heard anywhere from $50,000 to $200,000 an hour for a crewman's or a crew person's job.
Yeah, it's
and so you have to be very
135,000.
cognizant of that. And it's 135. Okay, cool. Thanks. But it's also extremely dangerous, right? So it's expensive and dangerous. And so if there are things that you can do with robots, then that makes it safer for the humans who are working. So it really kind of ties those. We see, you know, the work that Alicia's division is doing, and the inclusion or the incorporation of robotics is really being tightly coupled to our expansion into, you know, low Earth orbit, and then moving past cislunar.
Yeah, I appreciate that, Paul. I think sometimes with our space for Earth development, we forget that our space to space is a learning platform. We have been working with Regolith, the lunar soil simulant. Can't call it soil because it's not organic, so it's a regolith. But we've been working to understand how to 3D print with that so that we can make our in situ resources go farther for the Artemis mission and the moon. So really just understanding how things behave in a microgravity environment or a low gravity environment is invaluable. So whether we just keep it on the ISS or we take it to the moon or we take it to Mars, we have the physical understanding of how things heat, how things move, if we're going to have any malfunctions due to something floating away. And there you go, just how to keep it safe. So that when we get to the moon, we understand, can this be inside the habitat? Does this need to be outside the habitat? How much dust does it create? And so even though NASA makes it really painful to make everything as safe as possible, you know you can apply it anywhere after that. So it's a fantastic learning opportunity to operate there, whether it stays or we apply it to new things.
I'm just gonna open up the floor and say, if anybody has questions, queries, please like shout them out, put a hand up, dance around the room.
Yeah. Well, sure, I got a question. Obviously, 3D printing relies a lot on gravity, like just at least the 3D printing I know about. So how do you guys, fight that, like at least micro G, I guess it's not 0 G. How is that accounted for in the technology you're developing? Were you able to hear that?
Yeah, he wants the secret sauce, DJ.
What I will say is it's a good question, but the answer may not be as complicated as you think. When Made in Space at the time set out to design the 3DP, they had the same thought of kind of like, oh, what are the challenges that we're going to face? And so where they started was, let's just go buy a bunch of commercial 3D printers and put them on the parabolic flights, the vomit comet, if you will. And you're right, they found that there were some challenges with just taking a COTS printer and having it produce the same quality of parts in a microgravity environment. And so that led down an engineering path, and we were ultimately able to solve that through more microgravity or parabolic flight testing, which is very fun, by the way, if you ever get an opportunity to do that. And yeah, so we solved it, but it was not necessarily as complicated as you think. But yeah, that is part of the secret sauce there. Good question, though.
I believe there was a question.
So the cool thing is during those, just to add on to that quickly, the cool thing is that those parabolic flights, it's not just 0 G because, they do this parabola. And so it actually varies between 0 G and 2 G. And during those parabolic flights, Deejay, because this was before I joined the company, unfortunately, but Deejay and the team were able to show that they were able to print from 0 to, through the 0 G and the 2 G, which really kind of opens the door for, for higher than 1 G operations, which is very interesting as well.
Yeah, I actually was not involved in the initial parabolic flight testing that led to the 3DP design. But expanding on that, we did take the 3DP and we've tested it in some extreme environments as well, or sorry, the AMF, and tested it in some extreme environments. And as Paul mentioned, it is what we like to call gravity agnostic. It can print pretty much anywhere we put it. But the parabolic testing campaign that I was a part of was actually part of the experiment was demonstrating SLA printing in microgravity, which was very exciting and very challenging. And actually led to one of the projects that Alicia's team has been doing a lot of cool work on that. So I don't know, Alicia, if you wanted to jump off of that point, maybe talk a little bit about I think it's TCMM.
Yeah, for sure. just kind of going along this thread, anybody who's been in the lab and has done testing on hardware probably thinks what we do in our testing phase is pretty wild, because we'll actually turn it upside down and make it operate, and we'll put it on every single face of, we have to operate in a basically locker. So we put it on all the faces of the locker and run a test to make sure that it truly is gravity agnostic before we launch it. So we do that with all of our experiments, just to understand if there are any gravity induced benefits to being on the quote upside. And we have actually found some really interesting like thermal transfer benefits based on what side it's on. So helps us tweak it and make sure that it's truly ready for the gravity environment. And the SLA printing is really, it's just so cool to work with that, because if you think about it, you're like, you have a vat of liquid, like how do you do that in space, and how do you get that uniform? And unfortunately, I can't give you that secret sauce either, but you know, it's really comes down to material science at the end of the day. What material are you working with? How do you get it to behave in the manner that you want it to behave? And then once you know that, you can engineer a process to ensure that that happens. And so we have a really close relationship with our materials folks, because literally once you know the physics and that chemistry, depending on what you're dealing with, we have a group of fantastic engineers that can work with that. And so sometimes it's a matter of, you know, just how much do you need to control it? How much do you need to extrude? How much do you need to expose to the environment that's going to cure it or harden it? So we've sent up the SLA printer experiment twice now, and we've worked with 2 different pre-ceramic resins. And we have 6 more proposals out to look at 6 more resins, because we want to understand, you know, what's the best material for a flexibility application? What's the best material for a hardness application? Because this is something in a size that could go and travel in a deep space. If you don't want something from an engineering polymer, you could do something in ceramic. So just increasing those capabilities for whatever the astronauts and the explorers of the very near future are going to need. We want to produce that for them. Anything else you want to tag, Deejay?
I just had a question that I had to ask. Why SLA? Why not just stick with the layer print, the AMX? Why are you experimenting with SLA techniques?
Well, it opens up more materials and it opens up more geometries. Really, is the most simple answer. There are limitations to how much a polymer can do if you're going to add it into a system as you know, a blade or a disc. And you know, if you make a tool out of it, it has a strength limitation. So like I said, we're working on different polymers, different resins for ceramics, and we're trying to move into working with metal on the space station as well. So just expanding that toolkit of what the capabilities are as we get into deeper and deeper space, because we don't know what we're going to need and we don't know what's going to break.
Yeah. Oh, go ahead.
Sorry, you go. I was going to say there's a couple of questions in the chat. So when we're done responding to this question, I'm going to read them out. But if you have something to add, Deejay, please go ahead.
Yeah. I see them coming in, and I've been trying to steer the conversation back to answering those. So I'll get there in a moment. But kind of talking about this, you know, unique manufacturing things and finding unique solutions. I wanted to see if there was anybody in the room who had maybe considered pursuing systems engineering. I see a couple of hands. Yeah. So you guys are the folks that have to figure out how to ask the right questions and ultimately set the requirements to allow the engineering space to find unique solutions, right? So you might think that a solution has to be one way because, you know, conventionally that's how it's done, or maybe you've taken for granted that gravity is sort of an underlying assumption. But if you strip away those sort of solution specific language and the requirements and say, you know, we actually just need to be able to do this, it can let the engineers get a little more creative sometimes and find really interesting and unique solutions, like what we were able to do to make SLA printing work as well as traditional additive manufacturing and microgravity. So I just kind of wanted to put that plug out there because systems engineers, I think, are largely the glue when it comes to a lot of these aerospace projects. So, props to you guys, and I hope that you all have good careers there. We're certainly hiring a lot for systems engineers. So when you're ready, we have openings. So yeah, I think we could take it over to the chat questions.
Yeah, reading up first, we have, has Redwire thought about sending pre-manufactured modular panels and assembly robots to create structures in space?
Yeah, absolutely. That's a good question. It's an excellent line of thinking. Actually, Paul, do you want to answer this question? I think maybe this one might be better for you. Might be fumbling for the mute.
I actually didn't hear what the question is. What is the question?
The question was, has Redwire thought about sending pre-manufactured modular panels and assembly robots to create structures in space?
Oh yeah, absolutely. Absolutely. Yeah, the idea of having persistent platforms is what they are frequently referred to, on orbit is really something that people have thought about a lot, and they can be used for any variety of things, right? I mean, certainly having a 100-meter by 100-meter platform, which could be used to collect energy and then possibly beam that to the moon, because the moon is operations on the moon are going to require a lot of power, or down to Earth, because if you're above the atmosphere, that provides a lot more efficiency for gathering energy. Or so you could use it for solar panels, like you suggested, or you could use that as a backbone for the next version of Hubble, or a phased array. So there's a lot of different things that you could potentially do with a large persistent platform. And to me, it makes sense. So one of the things that we also think a lot about at Redwire is what we like to call the tyranny of the fairing, right? So the top of a rocket has this enclosure, which is called a fairing, and my apologies if you guys know this, and everything that's launched into orbit has to fit within that fairing, right? So these fairings are typically, I don't know, maybe 3.5 meters in diameter, and maybe a big one could be 9 meters tall. Actually, that would be an extraordinarily big one. But the point is that a 100-meter by 100-meter platform is not going to fit into that space, right? So you have to figure out how to deal with it, and one way is to have a couple of 3D printers that print smaller versions and then have those robotically joined together. So yeah, it's definitely something that we've thought a lot about and are actively working ideas on.
Awesome. I'm seeing another question in the chat as well. From
I think it's an essay.
well, first of all, from Salvador, we have, this tech could have made the Apollo 13 mission a little more comfy. I can't imagine how useful and downright necessary this tech would be considered in the future.
Yeah, actually, one of the really cool things that we did early on was we had one of our interns design a solution to be 3D printed for the Apollo 13 mission. And we used to use that as a demonstration of why this technology, having manufacturing capability in long duration space missions, or really any kind of space mission, is so crucial, because you can deal with those things. And actually, we have leveraged AMF for a number of things, both supporting experiments on the station as well as the station itself.
Yeah, I'm just going to tag on real quick. That's something that I'm not sure how many people know. NASA contacts us pretty regularly for this type of need. If anybody's familiar with NASA, they know that there are a lot of different NASA centers, and they all design different pieces that get sent up, or the mechanism to send things up. And so it's not uncommon that somebody has designed something and the adapter was a little bit wrong, or the measurements were a little bit off. And so they'll contact us and they'll say, hey, can you make a fan cap cover? Can you make an adapter for this hose to fit into, our vests, our way of getting gases out of the space station. So it's not super frequent, but I mean, every couple months they'll come up with like a little tweak here or there, so they don't have to relaunch something. So they can use something that's an upgrade to their life support system immediately, just because we are able to print an adapter for them. So I think the fastest we've ever turned it around is like 3 days. So we're able to do something like that and immediately improve the lives of the astronauts. So those are the most fun missions, I think, for us, because they're kind of a surprise, and it's a challenge to us to turn something around quickly and make sure that it works. And you get to see the astronauts plug everything in and be like, yeah, it's all good. So so that happens all the time.
Awesome. I believe our next question in the chat comes from Benjamin, who says, what is the plan to get the raw resources for large-scale on-orbit manufacturing? Would it be raw materials from Earth or Moon or from asteroids? Is that sourcing issue one that Redwire itself plans to solve? Or is Redwire hoping that other companies will eventually provide materials through a service of their own?
Yeah, really good question. And first, let me say, we would be happy to have you join us and help solve those challenges. That is something that we're working on, and that is, I mean, that's on the long-term application, right? Obviously, this isn't something that we have a solution for today, or I think we'd be doing it other than the Earth part, right? I mean, all of our Archinaut AMF. All of our payloads, they do get all of their materials from the Earth, and they're launched up. But really, the cool application is when we can start taking that from the Moon, from Mars, and from asteroids. And we've done a number of very interesting studies. Actually, me and some colleagues were actually talking about it today. There was a study that one of our aerospace engineers did, and I believe the sort of study that he did is public, and it's called RAMA, and it was this really interesting, far-looking technology where we could essentially go send a seed craft to an asteroid and turn the asteroid into a spacecraft to fly it back into low Earth orbit or somewhere closer that we could get to it and mine it. And so yeah, I mean, we are looking at current technologies all the way out to things as advanced and far-fetched as Rama. So yeah, we are looking at it. I think a recent one, if you Google, what was it called? Break the Ice Challenge. I believe that's what it's called, and it demonstrated some concepts we had for some moon mining based on sort of robotic tractors that could go be launched to the moon and collect materials to manufacture into things like launch pads and other things there. So we have other projects that we've worked on at some point. This one's actually near and dear to Paul. So Paul, if you want to jump in and talk a little bit about Rego bricks, now would be a good chance for that.
Sure. Yeah, so I mean, I think the answer to the question of whether we're going to resupply from Earth or use asteroids or lunar, the answer is yes, right? It makes the most amount of sense to use whatever is handy, right? So if you wanted to print things if you wanted to print bricks for use on the moon to make habitats or structures, you use the regolith that's there, as Alicia was saying, and then you'll mix that with polymers that you would bring from Earth, and the polymer is fairly light for volume, for unit volume. So you can bring up a lot of polymer and use the local resources, the local dirt, to make your bricks. But even more exciting, if you were to go to Mars, you can actually extract that polymer, the plastic part, from the Martian atmosphere. And so and use the local dirt as well. So what's really interesting is you have these opportunities. If you understand what the local, what resources there are locally, you really have these opportunities to use the local resources. And just to bring it back down to earth for a moment, if we wanted to build, structures on hard to reach places on Earth, it's the same thing, right? You could use the local sand or, whatever materials are local, and then bring in some, if it's a hard to reach place, like a desert, and you wanted to, some of the processes we've developed, you could use those local materials, sand, and then bring in polymers and make bricks out of the sand for far more cost efficiently than bringing in an actual brick. And of course, when you're on the moon, taking a brick to the moon is pretty expensive, and so it makes much more sense to do it there. But what's cool about it, and a lot of things, the other things that Alicia was talking about, like the crystals that she mentioned, growing those on orbit, a lot of the things that we're developing for use in space can also be really beneficial for here on Earth.
Are there more questions, Grace, from the audience?
Yeah, I think good one. So actually branching off of that, you've talked a lot about space manufacturing for products used in space. What are some examples or thoughts you have on space manufacturing for Earthbound products?
I'll just jump on Paul referencing.
But I think the question,
yeah, he was asking about space for Earth. So just jumping on the crystal manufacturing, there are a lot of different types of crystals that we use in application on Earth. So one of the ones that we chose to go with for our first experiment was something that we use as a laser lens and medical lasers. So you can do eye surgeries, and you need that laser to separate the light beams in a certain way to have a certain cutting effect for that surgery. So there are lots of different applications for crystals. And the problem with the earth-grown crystals that we have right now is that they have imperfections in the crystalline structure. So those imperfections will cause them to crack at an earlier point than potentially a more perfect structure could cause them to crack. So if we can extend the life of that laser and that procedure, then we can make the cost of that procedure lower or make that process more efficient. So that's one application of the crystals, but you basically, if you look around, you see them used in a lot of really heavy science research areas. They use crystals in fusion experiments, for example. So, not only medical arena, but, also in the energy arena. Like I was saying about the sedimentation effect, if we can heat treat metals or melt and reform metals, if it's a single crystal, then you can make that structure more perfect, make your buildings stronger, make your tools stronger. With the ceramics, if you could put a ceramic turbine into a system, higher pressure, higher speeds before it breaks. So increase the safety aspect and the efficiency of that machine. So there are a lot of different areas that you can apply it, but it's the same general understanding of you're fighting sedimentation, you're fighting the actual gravity on Earth that makes things less perfect. So looking for those opportunities in space is what we're doing, the manufacturing, and we're trying to move into the tissue growth and the bioprinting type field to understand how we can affect tissue directly and not just the hardware that helps support it.
Awesome. Another one from the audience? Probably do like one or two more.
I have one, if that's okay, which is, does Redwire or Main Space have a long-term goal?
Do we have a what?
Like, do you have like an ultimate goal?
Oh yeah. I think making humanity a multi-planetary species.
Yeah, I mean, Absolutely. And to expand on that, one of the metaphors that Andrew Rush likes to use is that companies like SpaceX and Blue Origin and these other launch companies, they're making the covered wagons, right? And that's an important step. But what Redwire is really focused on doing is making the pickaxes and the shovels and the tools, so that when we get to these planets, we can actually build colonies and habitats and persist both in orbit and on the planets. And so, technologies like Archinaut enable those large persistent platform manufacturing and assembly on orbit, and all of the payloads and ISS manufacturing capabilities really pave the way for all of that manufacturing capability that would be needed to support those things. So, and then, they both kind of blend into each other when it comes to robotics and things.
Yeah, and it's not just our group. We're all within a group that was previously made in space. Redwire is a group that has 7 companies, and they're looking to continue to grow that. And they've been trying to grab more companies that are very similar in that they have kind of specialized in the type of technology that they provide. We have the iRosa solar arrays. That's a Redwire company now. We have star trackers. We have digital engineering. We have cameras. I mean, all kinds of specialty products. So the idea is that Redwire would be able to essentially grow to the point where we can create our own complete space systems in a really specialized manner. So it's not a one size fits all of a prime that has a whole bunch of subcontractors that we're kind of each other's subcontractors. And it's an interesting place to be, because all of a sudden we have access to people kind of on a casual coworker level that before we had to have a contract and had to be very formal. So it's a neat environment, and I know that they're looking out for some more companies that fit that culture.
I'm seeing some relation with Redwire and what you just said, Alicia, with kind of the Amazon of this space development.
Yeah, there's keep watching the news for some developments on that. But yeah, we have been talking to Amazon quite a bit, looking for a great opportunity to partner with them. So in about a month, you should see some news.
We've got a question in the chat from Salvador again, who says, do you guys believe the dollars per kilogram value to get things into space will drop in a couple years and lead to a boom in our industry?
I would make the argument that has already happened. I mean, what was the launch cost value during the Apollo? I can't remember the number, but it was a huge dollar per kilogram launch cost, and we're down to I think
40,000.
Was it 40 for Apollo?
Oh no, 40,000 now.
Oh, I was gonna say it's even lower. I mean, you can get to spaces for as low as 15,000 a kilogram.
Yeah. Well, this is with NASA, so maybe one of the other providers is cheaper.
Yeah, but as an industry, we've gotten orders of magnitude cheaper already, and I would point to the number of aerospace companies that have popped up or have been making news in the last probably 5 years, as the boom has already started. There's an enormous amount of interest in the aerospace world, so it's a very exciting time to be in aerospace.
If I can expand on that, one question that we've been seeing a lot of people is the effect of Starship on launch costs. In the Space Shuttle was, I believe, $30,000 per kilogram. Falcon 9 is $3,000 per kilogram to Leo, and Starship supposedly, according to Musk, will be $300 per kilogram. I'm wondering if that affects your guys' business model and that's accounted for, or whether you intend to continue with existing launch providers.
I actually see that as all helping for us, right? I mean, it's all of that. Just again, we are complementary to all of the development in the world, in the aerospace world around launch vehicles. As things get cheaper, we can do more manufacturing, more resource mining, more cool stuff, because suddenly the access to space is just so much greater. So, you know, I see that all as just a good thing for the industry.
I think we have time for one more question. If people have one, throw it out. Now's your chance. Going one? Sure. Go on.
Yeah, so thank you so much for this experience. It's been really cool and really informative. I just got a pretty broad question. What career opportunities are currently open at Redwire and Maiden Space? Is it purely technical, or are there opportunities for people with non-technical backgrounds as well? What kind of people are you looking for?
All of them.
All of them.
Yeah, absolutely. So in our Jacksonville office, so you know, redwirespace.com is our website, and it does have a pretty good list of all the positions that are open. And really, you know, what's interesting, I think, about this, I think what's interesting about satellites and space in general is that the logistical challenges are almost as challenging as the technical challenges. And what that means is that not only do you need engineers, but you also need people who are able to, you know, work the supply chain, and people who are able to, you know, work the business aspects of it. So like Deejay said, it really is kind of all of them, right? I mean, for the three of us, Alicia, Deejay, and myself, we're more interested in the technical teams. We need, you know, aerospace engineers, systems engineers, software engineers, material scientists, electrical engineers, people who are good at FPGAs, you know, firmware engineers. Those are really important, but the business not only needs not only those folks, but those supply chain people, admin people. I mean, all across the board, it's there's lots of positions open. And what's cool about Redwire is, you know, if you're not a fan of Jacksonville or Florida in general, you know, we do have lots of facilities in Denver and one in Goleta. And we're expanding, right? So there will be other positions or other facilities here in the not too distant future.
And if anybody's interested, there are positions open in Luxembourg. So that could be fun.
Yep.
Yeah, and I think we've posted our intern positions, or we will very shortly. So if you're interested in internship, go through the website.
You can also send me your resume, and I'll make sure it goes to the right people.
Yeah, are you okay with that? Can we share your email to the audience that came today? Do you want to put it in the chat? How should we do that?
Absolutely. Well, I can't put it in the chat because I'm not on the chat, but Deejay, you can put it in the chat if you would, please. It's paul.shestople@redwirespace.com.
Gladly put your email and send all of the actions to you.
And I like Salvador's shout out to Paul's like first sentence. He said, "That's amazing. I didn't know that. You could do that for a living." So they were listening, Paul.
Exactly.
We've all been wondering. Well, you guys can't see me, but thank you so much for coming in today and taking the time out to talk with us. We're beyond stoked for it. And hopefully we can keep bringing you back and get a lot of people from Berkeley working at Redwire, working with you guys. You inspire us all.
Yeah, definitely. We enjoy being here.
Well, that's awesome. Thanks for having us. We definitely enjoy it.
Yeah, thanks everybody.
And let us know if you want us to recruit people with other specialties as well. If you guys have interests that are broader, we know people who do everything.
Great.
Thank you guys so much for coming. Just,
All right.
yeah, a round of applause.